In this video, we will learn how to solve improper integrals for Calculus 2. An improper integral is an integral that has either infinity or negative infinity in one of the bounds. It also is an integral that is undefined, such as 1 over 0. This is primarily characterized by a vertical asymptote. And a vertical asymptote, let's take this line for example. As I approach this line, right, this is just an arrow by the way. As I approach this line, I could come like this or I can come down. My function becomes undefined. And we don't want our function to become undefined. So in order to do that, we can evaluate it as a limit. So let's see what that all means. Let's take an example problem. Let's take the integral of 0 to pi over 30 of tangent 15x times dx. Upon looking at this problem, the average Calculus 1 student even is going to look at this and be like, well, let's just perform u substitution. Let's let u equal 15x and be done with it. Now, that is true. U can be tangent, or u can be 15x, and you could solve it like that. However, you need to take into account that 15 times pi over 30, which I got pi over 30 from one of these bounds, is equal to pi over 2. Now, we know tangent of 15x can be rewritten as sine of 15x divided by cosine 15x. Now, if we put in what 15x is, we get sine at pi over 2 divided by cosine at pi over 2. Now, if you know what the unit circle is and you know what pi over 2 is for sine and cosine, you'll know that sine at pi over 2 is 1 and cosine at pi over 2 is 0. This makes an undefined function because we cannot divide by 0. So we have to take the limit as a variable. Let's say t approaches pi over 30. I'll put t there. And note that pi over 30 is approaching from the left-hand side because we're going from 0 to pi over 30. The only values that we can get are going to be from 0 to pi over 30, and we're approaching from 0 to pi over 30. So we're going from the left-hand side, not the right-hand side. If we were going from the right-hand side, we'd be at values above pi over 30, but we want values that are in the integral from 0 to pi over 30. So let's rewrite this. Okay. So now this is where we can apply our u substitution. If we let u equal 15x and du equal 15 times dx, this will not work. This is why this u equal 15x will not work, because we have sine of 15x on the top. Now, in order to actually do this u substitution, we will need to do the whole entire bottom of this fraction. U equals cosine 15x. Now, the derivative of this gives us negative sine 15x times 15 gives us negative 15 sine of 15x. And this actually equals du still. So now what we can do is get rid of this negative 15 on this side by dividing it. And we get this. Now if you notice, the entire top of this fraction right here is sine 15x times dx. So now we apply our u sub. But first, let's just change our bounds before. Let's make u equal cosine of 15 times t. Now what is t? It's pi over 30 approaching from the left. So we know that it's really just cosine. Now cosine at pi over 2 is 0. Now let's do u equals cosine of 15 times 0. Cosine of 0 is just 1. So our entire integral is now, let's say the limit as b approaches 0 to 0. And this is approaching from the right-hand side because we are going from 1 to 0. Not from the left, but from the right. Now, applying our u sub, we can rewrite this as 1 over u times what we let the u equal, which was the negative 1 over u. So now we can bring out this constant to the front. We'll have the limit as b of 0 approaches it from the right, times negative 1 over 15, the integral from 1 to b. 1 over u times du. So now what we can do is we look at this negative 1 over 15, right? And we look at what our function is inside the 1 over u. We know that the integral of 1 over u is the natural log of the absolute value of u. So applying that, we now have the natural log of the absolute value of u from 1 to b. Now we just evaluate the upper and the lower. So let's do that. Let's keep the negative 1 over 15 out for now and just do natural log of the absolute value of b. The natural log of the absolute value of b. Let's look at what happens as b is approaching from the right-hand side, which would mean from the positive side. So if we plug in the natural log of 0.001 in our calculator, we get negative 6.9. Now if we plug in natural log of 0.000001, we get an even more negative number. This means that as we approach 0 and keep on getting closer and closer and closer and closer on the right-hand side, we get closer to negative infinity. Now the lower is the natural log of the absolute value of 1, which is 0. Now we apply f of b minus f of a equals negative 1 times upper bound of infinity times, or minus 0. Now looking at this, we can bring in the negative 1 over 15, jump it in twice. Negative times a negative gives us a positive, so it's now positive infinity plus 0, which is just infinity. So this integral diverges, which means that it does not have a specific finite value that it converges to. It instead diverges and just goes either to negative infinity or infinity. In this case, it's infinity. Hopefully that wasn't too bad. Now, let's look at a little bit more complex looking, different type of improper integral. Let's do the integral from 0 to infinity of tangent sine of negative 1 of the angle e to the negative 2x times dx. If we look at this, it looks pretty scary. We don't know what the integral of inverse sine is. However, we do know that inverse sine of e to the negative 2x is really sine of the angle equals e to the negative 2x. So applying that logic, we know that sine is just opposite over hypotenuse, right? So if we want to find what tangent is, we need the adjacent angle, because tangent is opposite over adjacent. We can do that by using the Pythagorean theorem. A squared plus b squared equals c squared. Plugging in our values for the opposite gives us e to the negative 2x quantity squared plus b squared with the adjacent equals c squared, which is the hypotenuse, 1 squared. Subtracting e to the negative 2x quantity squared on both sides, we get b squared equals 1 minus e to the negative 2x quantity squared. And to isolate for b, we can square root each side to give us our final answer for the adjacent angle. So now let's bring down our tangent of theta. We said is equal to opposite over adjacent. So we know that the opposite is e to the negative 2x. Adjacent is the square root minus 2x quantity squared. Now looking at our integral, we have the integral from 0 to infinity of, we want tangent, right? This is our whole goal. So we can just rewrite what we have as equal to tangent, right? No, my eraser's messing up. Okay. E to the negative 2x divided by the square root of 1 minus e to the negative 2x squared. Now you might be wondering, why did I not bring in this square, right? Why did I not bring that in there? It was simply because of this rule. Look, or not rule, but this method. If you look at the top and bottom, we have the exact same thing, e to the negative 2x and e to the negative 2x. This means that we can do our u substitution on this problem. Now before we do that, remember, this is an improper integral. Remember how I told you that an improper integral has either infinity in one of the bounds or the function is undefined. If you look at this function, we have infinity in the upper bound, right? So we need to rewrite it as a limit. Let's rewrite it as the limit as t approaches infinity from the integral of 0 to t. Oops, so that t, there, t. Now, infinity, we do not need to add the right or left for, like we do for the limit, like we did up here where we had the limit as we approach b, as we approach 0 from the right, like you see here. We don't have to do that because infinity doesn't really have a direction. The direction is whatever the sign of it is, which is positive, meaning I'm going positively to infinity without bound. So now we just rewrite what we had above, copy paste this down here, and you should be able to look at it and realize that we can just let u equal e to the negative 2x, right? And take the derivative of u using the chain rule. We get negative 2 e to the negative 2x times dx. Isolating for e to the negative 2x times dx, we get negative 1/2 du equals e to the negative 2x times dx. Now if you look at this numerator, it matches this perfectly. So let's change our bounds. Let's take u, we know it's equal to e to the negative 2 times t. Now, we know that t is approaching infinity, right? You can think of this as e to the negative 2 times infinity. Now, this is really just e to the negative infinity, and if you had a calculator, you could plug in values as you get closer and closer to negative infinity, you'd get the same answer. Or you can think of it intuitively as 1 over e to infinity. The top, or the numerator, stays the same. It's always going to be 1. But e to the infinity keeps on growing bigger and bigger and bigger in the denominator. This means that as we get closer and closer to infinity in the denominator, we go closer to 0 because we have a smaller number divided by a bigger number. So we get close to 0. Now let's do u equals e to our lower bound, which was 0. E to the 0 is equal to 1. Now we can rewrite the integral of 1 to 0 of 1 divided by the square root of 1 minus our u squared times negative 1/2 du. So now looking at this, we can still factor out our constant, right? And we get negative 1/2 from the integral 1 to 0, 1 over square root 1 minus u squared times du. Now, this formula right here should be screaming out at you as the integral of, well, not the integral, but the derivative for the sine function, right? Because we know the derivative of the inverse sine function is 1 divided by the square root of 1 minus x squared. In this case, it's u squared. So we know that this is going to be inverse sine, or the integral of it will be inverse sine. So we now have negative 1/2 times sine, right? And I'm going to just point this out just for future reference, that it's actually the sine of x over a, or the square root 1 over the square root of a squared minus x squared. Now the reason why we don't have to put x over a here is simply because if we look at the function, we have this a squared, right? If we look at what's here, this is just equal to 1. So 1 squared is just 1. So we can disregard a because anything divided by 1 is just the same thing as the numerator. So we don't have to write x over a, right? This is not correct. We don't, or it's not that it's not correct. It's just not necessary. Our variable, and then keep our integration bounds 1 to 0. Now let's integrate. Let's keep the constant negative 1/2 out, and let's look at the upper, right? So let's do the sine of negative 1 at 0. So let's go back to our unit circle. Looking at our unit circle, inverse sine is 0 at 0. Okay? So inverse sine of 0 is equal to 0, and the reason why is because 1, 0 is the coordinate at 0 degrees on the unit circle. Okay? We know that this is x and this is y, where this is sine. See how sine at 0 degrees gives us 0 as the coordinate? That's why. Now let's do the lower. So that's going to be an inverse sine of 1. So where is inverse sine 1? Or what coordinate gives us that? If we look at the unit circle, look at the unit circle, 0, 1 is at 90 degrees on the unit circle, right? Where this is our sine function, right? Or not function, but our sine coordinate, or a y coordinate, which is correlated to sine. Now 90 degrees on the unit circle is equal to pi over 2. So that's going to be our answer. It's going to be pi over 2. Now what we need to do is apply the last step, which is f of b minus f of a equals, bring down this negative 1/2, our constant from before, times the upper bound, which we found was 0, minus the lower bound, which we found was pi over 2. Doing this, if we jump in this negative 1/2 times 0, we still get 0, and we jump in the negative 1/2 times the negative pi over 2. The negatives will cancel, and we're left with pi over 4. Now this integral is a convergent integral, or it converges, because it goes to a specific finite value, unlike this integral, where is it, that we found up here. This goes to infinity, meaning it diverges. It doesn't have a number or value that it goes towards, or it gets, finite. Infinity doesn't have, it's not a number, so it just keeps going without bound. But down here, we have a convergent integral because it goes to a specific finite value, pi over 4.